بسم الله الرحمن الرحيم. Welcome to Tahar Scholar. We are الخميس 12 أكتوبر 2023 or in English Thursday the 12th October 2023 in Malaysia. So this is the second practical in our series Programming with Matlab. In the first practical our main topic was the data type matrices, and we have shown in the first section how to build a matrix manually, then by editing the elements, then in the second section we have seen how to initialize a matrix using functions, and the third section we have seen how to access an individual element or a group of elements, a submatrix. So now we are in the fourth section. So the topic here for whole practical is about matrices. And this is the fourth section, how to build a matrix from other matrices. And in this section, we will see 5 points. How to concatenate matrices, how to repeat a whole matrix to build a new one, how to repeat only the elements of a matrix, or columns and rows of a matrix. And the fourth point, how to reshape a matrix, how to change its dimension, and finally, how to extract a diagonal from a matrix, or how to build a diagonal matrix. So 5 points. We start with concatenation. So we have cleared the memory and the console, and we need a matrix to test it in this section, to use it as input in this section. So let's write A equals randomize rand I. So between all the numbers should be less than 10, and the size is 3 by 3. So this will generate a matrix A. From this matrix, we will build a new one by appending a column and then appending a row. So let's begin with a column. Let's write it. U equal 0, 1. So 0, 0.1, 0.2, and 0.3. And this is a column vector. Observe that the number of elements in the column vector U must be equal to the number of rows in A in order to append the vector U here as a fourth column, to append it as a fourth column. So we get a new matrix A equal, we open the bracket, write our first matrix A, big A, and we append the column vector U. And this is called concatenation. We append the vector, column vector, as a new column to the new matrix A. So let's type enter, and we get a new matrix. This is A, big A, the original matrix, and this is the new column we have just appended. So it's very simple. But always observe that the column you want to append must have a consistent number of elements with the number of rows to the matrix you want to append to. So the number of rows will not change, only the number of columns. You can of course append here not only a column vector, but a whole matrix with several columns. So for example, let's write it big B equals randomize E, the function rand E or rand I, a new upper bound, and we want here the same number of rows, so 3. The number of columns doesn't matter, for example 5. And we have our matrix B. We can build a new matrix by concatenation of A and big B. We will get a new matrix. And as you can see here, this is A, and here we have appended a whole matrix, but such that the number of rows in the two matrices A and big B is the same. You cannot, of course, append a matrix that has a non-consistent number of rows. It doesn't work. You increase the number of columns, but the number of rows will not change. Now let's see how to append a row. We have seen how to append a column. Let's see how to append a row. So let's call it C, small c equal bracket, the original matrix A. A is 3 by 3, A. We want to add a new row. So here we need a vector first, V, for example, and let's write it here. Linear space. Let's generate a new row that we want to append from -5 till 3, for example, and it must have 3 elements because we want to append it to A, and we get V. So this is the row we want to append to our matrix big A. So we write C equal bracket big A, and we use here semicolon to add this new row, and we type enter, and you can see our new matrix has appended the appended row V. We can also append, of course, a whole matrix. For example, let's transpose the matrix B. So B, the transpose of B is, it has 5 rows and 3 columns. The number of columns is consistent with the number of columns in A. So let's write it D, small d equal bracket A and semicolon. When you want to append rows, use semicolon. And B prime. And we close the bracket. And we type enter. And that's it. So it's very simple to append a matrix as new columns or as new rows. Must be consistent with the number of rows and the number of columns you want to append. This is for concatenation. Let's move to repeating a matrix. So let us continue with the second point, how to repeat a matrix. We have cleared the memory and the console. Let's regenerate matrix A to use it in this point. So around I not exceeding 10 and 3 by 3. What we want is to repeat this matrix a number of times in the first dimension, in the row direction, and a number of times in the column direction, in the second dimension. So we use a function for that called repmat. Repmat means repeat matrix, and we store the result in the matrix B. As argument, we give the matrix A and how many times in the first dimension we want to repeat our matrix, let's say twice, and in the second dimension, let's say 3. And as you can see here, our matrix, the same matrix, is repeated along the row direction and along the column direction 3 times. And we get, of course, a larger matrix whose size can be easily calculated to the given number of repetition in the first dimension by the number of columns by the number of rows, and 3 the number of times in the second dimension by the number of columns of the input matrix. So we get 2 by 3, 6, and 3 by 3, 9. Now let's move to the third point, repeating the elements, not the matrix, not the whole matrix. Let us say we want to repeat only one individual element. So let's start first with vectors. Row or column vectors doesn't matter. So let's say we have removed it from memory, so we enter it again, any vector u, for example, minus 1.03, 6.57, and minus 0.5. And let's add another element, 8.94. And we close the bracket, and we have our vector of 4 elements. The content doesn't matter here. Row or column vector also doesn't matter. We want to repeat each element a number of times. For example, 3 times. What we use a function called rep element. Rep elam or elam means repeat the elements. And let's store the new vector in W. And as argument, I give the vector u and the number of times I want to repeat the elements. So, as you can see, the first element has been repeated 3 times, the second element 3 times, and so on. And we get a larger vector whose size can be easily calculated, 3 by the number of elements in u. So 12 elements. We can do that also for matrices, of course. Let's say we want to repeat the element of each matrix in a submatrix, in a new submatrix, whose all elements are equal to that element. So 8 will generate a submatrix, 5 another submatrix, and so on. And we have to give, of course, as input the size of that submatrix. We use the same function rep element. We give as input our matrix A, and each element of the matrix A will generate a new matrix. Let's say has 3 rows and 2 columns, and we store the result in a new matrix. Let's call it C. And as you can see here, the first element has generated a matrix 3 by 2. The second element, same. The third element, and each element, as you can see here, they have here the same values. Let's change matrix, our matrix A, to see that more clearly, because here the elements are the same. Oh, it's okay. The contents here doesn't matter, but for more clarity, let's change our matrix to, for example, 1, 2, 3, first row, dot 1, dot 2, dot 3, or 0.1, 0.2, 0.3, the second row, and the third row, let's use negative numbers, for example, minus 1.5, minus 2.8, and minus 3.7, for example. And let's repeat exactly the same instruction, repeat element A32. And as you can see here, more clearly, 1 is repeated in a submatrix, generate a submatrix of 3 by 2, and 2 generate also submatrix 3 by 2, and so on. Each element of the matrix A, each element will generate a submatrix with the given size 3, 2. And the content of that submatrix is the element, the corresponding element. So here 0, 1, minus 1.5, minus 2.8, and so on. Now let's suppose we want not to generate individual elements, but columns. We want to generate, for example, the first column twice, let's say twice, the second column 3 times, and the last column of A only once. How do we do that? We use the same function. Let's clear the console, CLC, display A, again, for reference. Okay, so let's call it D equal rep element. We give as input the matrix we want to repeat its elements, but this time, as I said, we repeat the columns. The elements we will along the first dimension, along the row direction, will not be repeated. The whole column will be repeated. So we do 1. We don't want to repeat along the first direction. So we introduce 1. And in the second, in the third argument, we introduce how many times we want to repeat each column. So the first column will be repeated, as I said, twice, the second column 3 times, and the last column only once. And observe here that this vector has the size of the number of columns of A. We have 3 columns, you must have here 3 elements, or it will not work, it will be an error, because you are indicating how many times each column must be repeated. So obviously you have to introduce as many elements as there are columns in this vector, and it is a vector, not a number. So let's enter, and as you can see, the first column is generated twice, the second column 3 times, and the last column only once. We can do that, of course, for rows. So let's call it E. Repeat element A. The first dimension, we want the first row of A, let's say, for example, 3 times, and the second row twice, and the last 4 times, for example. So it is that in a vector, 3, twice, and 4. And in the second dimension, in the column direction, we do not want to repeat the elements, because we want to repeat the whole row. So we introduce 1. And as you can see, the first row 3 times, the second row 4 times, twice, second row twice, and the last row, as you can see, 4 times. So if you do not introduce 1 here, what will happen? Then the repetition of the element will be twice. So we will have this row, we will repeat it twice. So let's do that, for example, to show the difference. And as you can see, the first row is repeated, not the first row, not the whole row. So the element of the first row will be repeated in the second direction, each element of the row twice, and then the content is repeated 3 times. And we do the same for the second column. Each element is repeated twice in the second direction, and then in the first direction twice, because we have here 2, so twice. And the third column, each element of the third row is repeated twice in the second direction. Each element of the row is repeated twice. And in the row direction, as we have indicated here 4, it will be repeated So if you want to repeat columns or rows, introduce 1, not 2, in the corresponding dimension. So we have here 1 in the second dimension because we want to repeat rows, and here 1 because we want to repeat columns. That's it for repeating the elements of a matrix by rows or by columns or individual elements. Let us move to the next point, how to reshape a matrix. So let's clear the memory and clear the console to start fresh. And reshaping the matrix means you change the dimension of the matrix, but not the contents. The contents will not change. And this is very useful if you have, for example, a vector and you want to change it to a matrix, a row vector or a column vector, and you want to change it into a matrix. But the contents of the matrix will be the same as the contents of the vector. So let's do that for an example. Linear space, an arithmetic sequence with a given number of elements, started from, for example, -5 till, I don't know, till 7, and it has 12 elements, and we generate it. So we have here an arithmetic sequence, and we want to change the vector to a matrix. What we do, we call the function reshape, and as argument we give the matrix U and the size of our matrix. The size here, be careful, must be such that the number of elements will not change. So for example, I can write 3 by 4 or 4 by 3, but not 3 by 5, because if I write 3 by 5, I get 15 elements, or 3 by 2, I get 6 elements. So the number of elements will not be changed. And we store the result in the matrix A, and we type enter. And here observe, because I have said before that matrices are stored by column by columns. So the first column will take the first 3 elements, the first column, and then the second column 3 elements, because we say here we introduced here, I mean we have given here as input 3 rows, 4 columns. So each column must contain 3 elements. So we get 3 elements from the vector to store them in the first column, and then 3 elements from the vector, the next 3 elements in the second column, and so on. We have reshaped the vector into a matrix, but the size of the new matrix must be consistent of the number of elements of the vector. We can, of course, reshape also matrices. We can, for example, reshape the matrix A instead of 3 by 4, 4 by 3. We have not changed the number of elements, but just the dimension. This is the condition to use a reshape. You should not change the number of elements. So let's say B equal reshape. We give as input A and the new dimension 4 by 3. 4 by 3. And we type enter. And as you can see, the underlying array, the array where the elements are stored, has not changed. But here, each column contains 4 elements. Each column contains 4 elements, the number of rows. So we take here the first 4 elements in our first column, and then the subsequent 4 elements in the second column. And the last, let's highlight them here, the last 4 elements in the last column. So this is for reshaping matrix. We have seen concatenation, repetition of whole matrix, repetition of elements of the matrix, individual elements or rows and columns, and the fourth point, reshape a matrix without changing the number of elements or the contents of the matrix. The last point is how to generate a diagonal matrix. So let's clear again the console and also the memory. And we will use in this section a function called diagonal. Diagonal has two functions, has two tasks, two different tasks. The first task is to generate a diagonal matrix. In this case, you have to give a vector containing the elements of the diagonal. For example, 1, 2, 3, 4. So in the diagonal, there will be the elements 1, 2, 3, 4. And we close the parenthesis and we store the result in a matrix. Let's call it A. And as you can see, we have the elements of the diagonals equal 1, 2, 3, 4. All the rest is 0. We can also generate with the diagonal the I matrix, the identity matrix. So the ID, if you remember, in building, in initializing the section, initializing a matrix, we have used a function called I, 3 by 3, for example, whose all elements are equal 1. You can do that with diagonals, it's equivalent. So you can write diagonal, diagonal, parenthesis, and here the elements here are all equals 1. So 1, 1, 1. And we get the same. Or we can also introduce, because all the elements are constant, we can use the function once, and we give it a row vector, dimension of a row vector or column vector, doesn't matter. So, but the number of elements is 3. So 1 by 3, or 3 by 1. And we get the same result. So this is the first task of diagonal, is to generate a diagonal matrix. The function diag or diagonal will generate diagonal matrix. The second task is to extract the diagonal from a given matrix. Let's say B is let B a new matrix, random real numbers between 0 and 1, and has a dimension 4 by 4. So we have here a randomly generated matrix 4 by 4, whose elements are randomly generated between 0 and 1. We have already seen random in the second section, in the first practical. But we want here to extract the diagonal elements. What we do, very simple. Let's store it in a vector U, and we call it diagonal. And we get a column vector containing the elements of the diagonal of the matrix B, stored in a vector, column vector. And that's it for this section, how to generate or how to build a matrix from other matrices. We have seen concatenation, repetition of matrices, repetition of elements, reshaping the matrix, and the fifth point, diagonal matrix. Let us move now to the fifth section. So in the fifth section, we study how to implement the inner product of matrices. In Matlab, just multiplication is called multiplication matrices, but in algebra, the term is inner product. So the operator is star. The operator is star. This is the operator to perform multiplication of matrices, like numbers, like any numbers. But the operands, let's say for example A and B, star B, two matrices, they must obey a condition. The number of columns, the number of columns in A, which is size of A in the second dimension in the column direction, it must be equals to the number of rows in the second operand in B. That is, size B equals 1. Again, the number of columns in the first operand in the first matrix must be equals the number of rows in the second matrix, in the second operand. Otherwise it will not work. The number of rows in the matrix, in the first matrix, and the number of columns in the second matrix doesn't matter. They will give the size of the result matrix. But the number of columns in the first must be equal in the number of rows in the second. This is mandatory. So let us start first with multiplication of a vector with a vector, and then a matrix with a vector, and then a matrix with a matrix. So let's introduce our input. Let's prepare our input for this section. Vector U is a row vector, 1, 2, and 3. Point 1, point 2, point 3, a small vector, enter, and the second vector V, let's say 1, 2, and 3. The same size, because when you multiply vectors with each other, they must be the same size. So here we have a row vector U and a column vector V. We cannot, as I said, in Matlab, the concept of vector doesn't exist. It is a matrix. A vector is a matrix of one row or one column. So the size of U is 1 by 3. That is, it has 3 columns. And the size of V is 1 by 3. It is has also a 3 column, but one single row. And to do U star V, it will not work, because the number of rows in the second matrix is not equal to the number of columns in the first matrix. So what we do the transpose of V. The transpose of V will become 3 by 1. And we get a scalar, 1.4. So if you want to multiply two row vectors with each other, you must transpose the second vector. And if, let's say, we have column vectors, you transpose the first vector to obey the rule that the number of columns of the first matrix must equal the number of rows of the second matrix. This is mandatory whenever you use multiplication stuff. There is, fortunately, a function called dot, because the inner product in algebra is called dot. You say A dot B, not A multiplied by B or A times B. In matrix, it is multiplication. So you just call dot U and V. U is a row vector or column vector, it doesn't matter. V the same. You can use dot with column, both vectors. The two vectors are both row vectors or both column vectors, or one is a row vector and the other column vector, doesn't matter. Dot will always work. So we get 1.4. This is also called the scalar product, because it produces a scalar. So this is for vectors. And I prefer, when I manipulate vector, to always use dot. But if you have to use the multiplication, make sure the rule of the number of rows of the first matrix is equal to the number of columns of the second matrix, because you are manipulating matrices. A column or row vector is a matrix. So let us move to multiplication of a matrix with a row. So we have already U, the vector U, and let's introduce the matrix A. Let's, for example, I don't know, let's check my notes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, for example. So it is a matrix, the size of which is 4 by 3. So let's check it with size. We have 4 by 3. And we want to multiply the matrix A with U. It doesn't work because U has only one row. And we have said that it must have the number, it must have exactly the number of columns in the first matrix. That is 3. So what we do, we change the transpose U to become a column vector. So now the size of U is 3 by 1. Is 3 by 1. So the first matrix, the number of columns must correspond to the number of rows of the second matrix. And then we can perform the multiplication, the inner product of a matrix with a vector. As you can see, the result. The result is obtained by multiplying, let's clear the console here. So A, U, and A star U. Now what we do, we take the vector U and we multiply it by the row vector, by the first row vector. The inner product, the scalar product of the first row of the matrix A with the vector U to get the first element. That is the first row with the vector U, the dot product, scalar product, will give us the first element of the product of A and U, 1.4. And if we multiply, if we dot the vector U with the second row dot the vector U, we get the second element. And say the vector U with the third row, we get the third element. And so on. The fourth row with U will get the fourth element. We can repeat that here. Dot of the second row with U, dot of the third row with U, dot of the fourth row with U, and as you can see. So the multiplication of the matrix with the vector is actually the dot product of the vector with each row of the matrix. And you get, of course, a vector that has the number of elements equals the number of rows of A, the number of rows of the first matrix. This is the inner product of a matrix with a vector. Let's clean again the console and see the product, multiplication of a matrix with a matrix. We have already the matrix A. Let's generate another matrix B. For example, it must have 3 rows, because the first matrix A has 3 columns, but the number of columns in the second matrix doesn't matter. So we have 1. Oh, we have made a mistake. 1, 2, 3, 4, 5. 1, 2, 3, 4. We have made a mistake here. It's okay, no problem. We repeat it. So the first row, and let's copy the second and the third row, CTRL-C, and we paste it CTRL-V, and we type enter. So we have our matrix of 3 rows. As I said, the second matrix must have the same number of columns in the, the number of rows in the second matrix must be equal to the number of columns in the first matrix. This is just the only condition you have to care of. So let's do A star B, and let's store it in C, and you get the new matrix. So the size of C, the number of rows is equal to the number of rows of the first matrix, and the number of columns is equal to the number of columns of the second matrix. That's it. But the contents, what about the contents? I've seen the size, the rule to observe when you multiply 2 matrices. But what about the contents? The contents is very easy, very simple. Each column of the second matrix will be multiplied by the first matrix. Each column is a vector. You multiply a vector by a matrix. We have already seen that. You multiply the vector by the first row, then by the second row, then by third, and you get a new column vector. So let's multiply the first column, B, with the matrix A, and let's check that it is equal to the first column of C. So let's say A multiplied by the first column of B. We should get the first column of C, and that's it. That's exactly the same. We do the second column, so each column of B will generate the corresponding column of C. The second column of B, the matrix A is the same, will not change. The whole matrix A will be involved in the multiplication, but each column of B will generate the corresponding column in C. So B2 will generate C2, the second matrix of C. And you can, for example, check, say J equal 3, and C, the column J minus A dot B, column J of C. The column J of B, the jth column of B, multiplied by the matrix A, must be equal to the column J of C, the jth column of C. So that the difference must be equal to 0. Whatever G is, G1, J equal 1, J equal 2, till J equal 5. So let's do that. And as you can see, equals 0. If one element is not equal to 0, then the rule is false. We have made a mistake. So let's repeat it for j equal 4. Same. And j for j equal 5. Same. Because when you multiply a column, a j column of B, of the second matrix with the first matrix, you get the j column, the corresponding column in C. This is the meaning of the multiplication of two matrices. And that's it for the fifth section. Let's move to the sixth section. So in the sixth section, we study the element-wise operations. Operations that are carried on each element of the matrices, of the operands. So the two matrices, here the condition of size, the two matrices must have exactly the same size, the same number of columns, and the same number of rows. So these operations are addition of matrices, subtraction, multiplication element-wise, are not multiplication of matrices. Multiplication matrices we have just seen in the previous section, it has a different meaning. It's not an element-wise operation. But if we want to multiply two matrices element by element, we use dot star. Dot star. It's actually two operators together, a pair of operators, dot star. And if you want to divide the elements, we use dot division, dot slash, divide. But dot means element-wise. And if you want to calculate the power of each element of a matrix, we use dot power. Now let's see these five operations through an example. We need first to prepare our input. Let's say matrix A equal random integer to check the result easily. Because if you write with real numbers, it will be difficult. Not difficult, but to check that visually easily, we use random integers. Should not exceed 10, and the size, any size, for example, 3, 5. This is for the matrix A. And for the matrix B, let's say randomize 100. The elements will not exceed 100 with the same size. Here, the same size is mandatory when you use element-wise operations. And for example, A plus B, we get a new matrix, exactly the same size, and the elements, so we can check here, 8 plus 74, 82, 6 plus 63, 69, 5 plus 56, 61, and so on. Each element of the first matrix is added to the corresponding element in the second matrix. Element-wise means element by element. That's it. And we do same for subtraction. We get, for example, 9 minus 77. We get minus 68. 7 minus 43. We get minus 36, and so on. For element-wise multiplication, not star B, not star B. If you do that, you get an error of the size. Size is different because not the size is different. I mean, the rule of the size is not satisfied because the first matrix has 5 rows, 5 columns. I mean, first matrix 5 columns, and the second matrix 3 rows. It doesn't work. It's not the inner product. So if you do that, you get an error. Non-conformant arguments. So the first first operand of 1 is the first operand or operand is 3 by 5, and the second is 3 by 5 also. So the number of columns does not correspond to the number of rows. But that's not what we meant. We meant element-wise. Element-wise, you have to introduce dot. So dot multiplication. And here it works, of course. You multiply 8 by 74, you get 592. So 8 multiplied by 74, you get 592. Or, for example, 5 multiplied by 56, 5 multiplied by 56, you get 280, and so on. Element-wise, element by element. And we can do that also for division, element-wise division. I mean, not this one. I beg your pardon. To write A. I am not used to the keyboard because I used to use a French keyboard, but it's okay. And actually, the QWERTY keyboard is better, far better. So we have our, and we can also check, for example, this element, the second row and the second column. So let's say A2 divided by B2, comma 2. We get exactly the same rate, C, comma 2. So we have not stored the matrix. So let's do it again and store it in matrix C. And we can check C2 is exactly the same. It's element-wise division. But when you use number, of course, you use just division. When you use matrices, you have to add dot to say that, to express that it is a element-wise division. And finally, let's clear the console. We have A and B. The last operation is the power. So let's say A, and let's store it in C. A dot power 2, for example, the square of each element of A. Not the square of A here, the square of each element of A. Not A, it's not A dot A. It's not the same. And A dot A will not work because of the number, the rule of size will not work. The number of columns must be, of the first matrix must be equal to the number of rows in the second matrix. So it has no meaning. But here it means the square of each element. And we get, as you can see, 864, 39, 749, and so on. We can also calculate the square root on 0.5, and we get the square root of each element. There is a function actually called square root, square t. You give it a number, for example 8, it gives the square root of the number, but also it works with matrices. You give it the matrix A, it gives the square root of each element of the matrix. So you can use the square root of A, or you can use A dot power 0.5. And that's it for the section related to element-wise operations. Let's move to the final section, some utilities Let's see some utilities with matrices. Let's clear the memory and clear the console. So in this section, we will see the sum, function sum, the minimum or maximum, function min and max, and the norm of a matrix. There are many others. You can check them in the documentation if you want. But these are the most important, and we will probably use them in the future practicals. We are doing all this actually to understand Matlab in order to perform, to practice in the practicals, to implement algorithms we study in the lectures. That's the goal of this appendix, of this series. It's not by itself. It's not just to study Matlab. It's to use Matlab to understand numerical analysis. So we cannot see all the built-in functions. It's impossible, of course, and it's not pedagogical. It will overwhelm you. So let's just see some utilities, these ones. So let's start with sum. As usual, we prepare some data and we start. So let's say A equal around I with integers and not exceed 10, 3 by 5. So matrix, 3 rows, 5 columns. Enter, and we have our matrix that we use to show how to use the functions. So the first function is sum. Sum, what will do? It will calculate what sum will do. It will calculate the sum of each column. So it calculates the number of the first column, all the numbers, the sum of all the numbers in the first column, in the second column, and so on. And we get a row vector containing the sum of each sum of the elements of each column. So let's write it, sum A, and store it in a vector U. And we get, as you can see here, 9 plus 8 is 17, plus 7 is 24, and 2, 7, 9, plus 2, 11, and so on. If we want to calculate the sum of all the elements, we can use sum of the sum of A. And we get the sum of all the elements in the vector U, which is also the sum of all the elements in the matrix A. So the sum works by columns. And the second is the minimum. So let's calculate V is the minimum of the matrix A. What does mean? What does mean do? It calculates the minimum value in each column and report it in a row vector. So the vector V, each element of the vector V is the minimum of each column. It works also by column. Let's do that. So the minimum here is 7, the minimum here is 2, the minimum here is 4, as we can see here. The minimum in the fourth column is 1, and the minimum element in the last column is 2. Same for max. If you want to store the maximum elements for each column, you call max. And that's it. So the next important utility is the norm of a matrix. So let's first see the norm of a vector. and then we see the norm of a matrix. There are, of course, different ways to define a norm. A norm is always a scalar. And let's first define a vector and see the norm through this vector. So vector minus 0.3, any vector, but we use a small vector in order to check our result easily. So 0, 0.25, and 1.45 and 3.75. And we close the bracket, we have our vector. The norm, the default norm of a vector is the Euclidean norm, what we call the Euclidean norm. And so its value is 4.0423. What is that? What does it mean? We know the norm, the Euclidean norm, or also called norm 2, you can also call it norm. The second argument by default is equal to, you can also mention it directly, explicitly, I mean, norm 2. So it's the second, or the norm 2, number 2, or the Euclidean norm also. Its meaning is, if you take the dot, the scalar product of the vector u by itself, and you get the square root of that scalar. That's the norm of the vector u. It's the length of the vector in a space of 3-dimension, vectorial space of 3-dimension or 2-dimension. It is the length of the vector. Its a general meaning is the inner product, the square root of the inner product of the vector by itself. So let's see here the same value. So this is the Euclidean norm, or the norm number 2. There is also norm number 1, or first norm. So let's write it, norm m, u, and the second argument, we say 1. And we get also, of course, the norm is always positive. And what does that mean here? Let's take the absolute value of the vector u. The absolute value of the vector is a vector whose elements are the absolute value of a given vector. So we get the absolute value of each element. And this is the absolute value. So minus 0.3 becomes 0.3. All the negative numbers becomes positive. And the others are unchanged. And we sum all the elements of the absolute value of all the elements of u. So sum of the SU. So the absolute value of the first element plus the absolute value of the second, and so on. This is the norm of the first norm. It's exactly the same number. The first norm of u is the sum of the absolute value of u, of the vector. And the third type of norm is the infinity norm. And here we introduce a string. We will see that in another practical, probably the next practical. We can introduce a string, infinity, using prime or double prime. Better, because to avoid confusion with prime as transpose, it is better to use double prime. In other languages like C++ or C, a string is defined inside a double prime or double quote. Okay, so let's type enter. We get another definition of the norm, another concept of the norm, and here it is actually the maximum value in the vector absolute u. That is the maximum absolute value in the vector u, in the given vector. So ABS u, and as you can see, so the first norm and the infinity norm are based on the absolute value of u. The first norm is the sum, and the infinite norm is the maximum. The norm, of course, has some property and is very useful to measure, to give like a length. The length has a meaning in 3-dimension or 2-dimension, but it assesses the length, somehow the length of a vector. So it is always positive, and it is of course a scalar. It is independent of the reference. You can change the reference, but the norm of a vector will not change. So the coordinates, you can change the coordinates of a vector according to the reference, but the norm will never change. It is an invariant. So it's very important in many applications. So let's clean the console and see the norm of a matrix. So as usual, we need a matrix or a vector as input to experiment with. Here we need a matrix. So we reshape our original vector into a matrix of 2 rows and 3 columns. And let us calculate on the first norm, the norm 1 and the infinity norm. So the norm 1, and see its meaning. The norm 1 is also scalar. If we calculate the absolute values, the absolute value of each element in the matrix, we get a new matrix, and then we sum the absolute value by column. So let's do that. Sum of the absolute value of A. As we said, sum will create a row vector, each element of which is the sum of the element in the column. So the element in the first column, the absolute value, are added in each column. The absolute value in each column are added to generate the sum of absolute A. So here, for example, 0, 3 plus 0, 15, 0 plus 0, 25, 1.45 plus 3.75. And let's calculate the maximum in this sum, this vector generated. Now let's write here, repeat the same operation and calculate the maximum. And as you can see, it is equal to norm 1. So the significance of norm, the first norm, is the maximum absolute, is the maximum sum of the absolute value per column. So we work here with columns. You get the absolute value of the element in each column, you add them, and then you get the maximum sum. Now this is the norm 1. The norm infinity, we work with rows. Let's do this. Is exactly but similar, however, with rows. So we calculate the absolute value, we determine the absolute value of each element in the row, and we add the element, the absolute value in that row. We do the same for the second row, and we get a vector, a column vector. and the maximum value in that vector is the infinity norm. How we can do that? Because sum works with column, doesn't work with row. We can do that very easily using, let's calculate the norm infinity first. So it's 4.15, and we can do that exactly as we have done with A, but we transform A to its transpose. So the column becomes a row. Each column becomes a row, and we get the infinity norm. So as you can see, exactly the same. We work with the column, first column of the transpose, because the first row of A is the first column of the transpose of A. The second row is actually the second column of A prime, of the transpose of A. That's why it works. So this is the first and infinity norm. There is another norm called the Frobenius norm. The Frobenius norm, let's calculate it first. Frobenius, I introduce Frobenius. Frobenius is a mathematician, and we get 4.0423. Now what is the meaning here? The meaning here, as you can see, it's exactly the norm of U. The vector where we store the matrix. Exactly the same. So actually, Frobenius norm is the square root of the sum of the square of each element of A. So we can do that here, square root of the sum of A dot power 2. So here we square each element-wise. This is an element-wise operation. We square each element of A, and then we calculate the sum by columns, per column. And we get then a row vector. Then we calculate its sum. So we get a scalar, which is the sum of all the elements squared in A. And then the square root. This is exactly the Euclidean norm of the vector U. Exactly the same. There is actually a fourth type of norm. So we have first norm, infinity norm, Frobenius. The fourth type is the norm 2, like norm 1 and like norm 2 for vector. There is also norm 2 for matrix. But the meaning here is more complex. Norm 2 is based on the singular value decomposition of a matrix. Singular value decomposition of a matrix, or also called the SVD of a matrix. SVD and eigenvalues and conditional numbers are a little bit advanced in numerical linear algebra. So before to finish this section, there is other utilities that are important for matrices, like the determinant of a matrix, the rank of a matrix, the LU decomposition, lower upper decomposition of a matrix. We will see that in chapter 2 when we study Gauss, because all these functions are based on Gauss decomposition. So we see that this is not advanced, this is basic linear algebra. We will see that in chapter 2. So we have finished data type matrix. Before to end this practical, let's write a script, small script, to test what we have already learned. We have seen 7 sections: how to build a matrix, how to initialize it through functions, how to access an element or a group of elements to submatrix, how to build a matrix from other matrices, the inner product, and then the element-wise operations, and the seventh section in some utilities we have just seen right now. So let's go to the editor. So in the last section of this practical, the eighth section, let's see how we can practice what we have learned in the first and second practical. We will write our commands in a script, not in the command window, so that we can save all what we write in a file. The files in Matlab have the extension m, so .m. So this is the interface of the editor. There is some button here to open and to save your file, to print it, and here for the copy paste. And the last one is for debugging your code. We'll see that later for debugging. Debugging means to find error, logic error, not syntax error, logic error in your code. These are actually useful when you have a really long and complex file, which is rarely used in Matlab. Matlab generally the code is short. Complex code is in C++ or Fortran or I don't know other languages, compiled languages, Java, etc. So the interface is very simple and common in any editor. Let's focus on the script. So what we want to do here is a small experiment. We want to generate a matrix with a given size, and such that the elements in the matrix are randomly generated inside the given interval. The given size of the matrix and the given interval for random numbers are given by the user, not hardly coded. So how we do that? First of all, always a good practice is, or good habit, is to clear, when you start your script, clear the memory, existing memory. So, and you clear the console. And then we use a function called input. Input asks the user to introduce a variable, and it stores it. So that's you can add a message. It's optional. A message. For example, here I ask the user to introduce the size, and I wait for the user to introduce it. And when introduced, I store it in AB or MN. I store it in MN and a semicolon to finish the command. What does this command do? Let's copy and paste it in the command to execute it, or we can use F9 to execute, run the selection, to execute what we have selected. Run. So let's go to the command. As you can see, it outputs the message we have given to the function input, and it waits for the data you want to input. You can only input one thing, so not a list of things. We can here input a vector of the size, for example, 3 and 5, 3 rows and 5 columns, and we type enter. And let's see what we have in MM. We have the vector 3, 5. So very simple, very easy. Let's come back to the editor. And we do exactly the same. Copy and we paste. But this time, not the size, the interval. And we save it in AB. We check. Okay. So in M is the number of row. We store the number of rows of the matrix, and n, the number of columns of the matrix, so the second element of the vector. So what we have here, okay, Mn, and we do the same with AB. AB for the interval. This is the start of the interval and the end point of the interval. We can also check if A is less than B. We use a function called assert. Assert checks if A is less than B. Because this is an input by the user, you could make a mistake. For example, instead of writing -3 till 1, you want your numbers between -3 and 1, you have accidentally written 3, 1, not -3. It will not work, of course. So we can check the input A less than B. It must be A less than B. This is a Boolean condition. If it is false, if A, I mean B, if A less than B is false, assert will stop the script and will display an error message. So it is very useful to check the input from the user. And then we write our matrix. So it starts with A, randomly generate numbers between 0 and 1, and the size is Mn. And we multiply the elements of the matrix by the length of the interval. So B minus A. Always, when you write a script or function, try always to finish your command by semicolon to avoid unnecessary display of the variables. So we have finished the matrix. Let's display it with the command disp. Disp will display the matrix and come back to a new line. So display the minimum. Let's display the minimum of each column. We have already seen function minimum. So message minimum. And let's display the minimum. It will calculate the minimum of each column and put them in a row vector. So it will display a row vector. Okay. Same for the norm. I've already seen that there is 4 types of norms. Let's display them. So norm. Let's display. We'll come back to those things later in another practical because there are many details. So display norm array. The two norm or the second norm, the one norm, the infinity, and the Frobenius. And the Frobenius. And that's it. Very simple script. It's like a hello script, because Matlab is about matrices. We have written a simple experiment with a matrix. We prepare the data, we do our experiment, and we display. Generally, the scripts are always like simple scripts. You prepare the data, you do your experiment. It is very simple. We generate a random matrix with a given size, and we display some information on the matrix. matrix itself, the minimum of each column, and the norm with its variance, different kind of norms, and save it. Let's save it. So we have save as dialog. Let's increase it a little bit. And we go to the documents, to numerical practicals. It's always useful to organize your data. So if you follow me, there aren't many people following currently. But anyway, if you follow me, try to have a folder dedicated to practicals, because we will write several scripts and functions. This is the first script. So I called it folder numerical methods NMS practical appendix A. This is the appendix. It is dedicated to programming with Matlab. And let's call the script matrix 1. You can call it, of course, what you want. Matrix 1. And it will add automatically M. So let's save it. And to execute it, the directory where the file is stored must be the current directory. So let's execute this button. Will execute the file, will run it, and the dialog will pop to say you change to the current directory. Let's say OK. Now the current directory, it contains only one single file, and the first command input asks us to introduce the size. Let's say for example 35. OK, 35. And we type enter. And for the interval, let's say -3 till 10, for example. So we want random numbers between -3 and 10. And we type enter. And as you can see, matrix A is generated. It has 3 rows and 5 columns. The numbers are randomly generated between -3 and 10. Now we can check here 7, -0, -1, 3, 8, 9, -0, and so on. The minimum per each column is calculated in the vector just below. So the minimum of each column. And the 4 types of norm. This is the norm 2, which is based on the SFD, as I said, singular value decomposition. This is the norm 1, infinity norm, and Frobenius. And with that, we end our practical. Inshallah, next practical will be on the other data types, strings, structures, and cells. I will try to be concise and brief, because they are not very important, but they are important anyway. Matrices are the most important, and I think I've showed you all the basics you should know about matrices in Matlab. So see you inshallah next time. Peace.